Here we'll look at a mathematical law called Coulomb's law, which governs the strength and direction of the electric field around source charges. You may notice that it's very similar to Newton's laws for universal gravitation. It shares the exact same format. Newton's law for universal gravitation was Fg equals g m1 m2 over r squared. Because of the division by r squared, the strength of the force got weaker the farther apart the two masses got, and the same thing will happen here with point charges as well. There was also a Newton's law for gravitational field, and for that we just drop off the second mass and we have gm over r squared. And there's a similar law here for the electric field. Now, whereas the gravitational force uses big G, which is the gravitational constant, Coulomb's law will use a constant called K, and Ke is going to be 8.99 times 10 to the 9 Newton meters squared per Coulomb squared, whereas G had the units Newton meters squared per kilogram squared. So there's some strong similarities in the mathematics here. What we're going to do is we're going to calculate an electric field strength using this law here. So let's try that now. Imagine you're located in space near a positive electric charge. And let's assume that this charge is actually a point charge. The distance between you and the charge needs to be found in order to calculate the field strength. So it's 4 meters between you and the charge. The magnitude of the charge is given as 1 microcoulomb. All right, so first we're asked to find Q. Q is the variable that stands for the magnitude of charge. How many coulombs is this charge? And I'll write that here as well. Q is the source charge that's exerting the electric field here. O is the origin. It's going to be the position at which we're evaluating the field. That's right here. So that's at a location of 0 meters if you go by the scale here. X equals 0 is where the person's standing. That means this is going to be -1, -2, -3, and -4. We're also asked to find X, the position of the charge. That's at -4 meters. We want to find R, the radial distance between you and the charge. We need to know this distance. To do it, all we have to do is subtract. So R is going to be 0 minus -4, which is 4 meters of distance between you. Lastly, we're asked to find the electric field strength at your location. To do this, we'll use the law E equals KQ over R squared, where Q is the source charge that's exerting the field. K is the Coulomb's constant. So we'll do 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. we'll multiply by our magnitude of charge. Okay. And then we'll divide by 4 meters squared. I get approximately 560. Notice that our meters squared here will cancel, and one of the coulombs above will cancel with one of the coulombs below. That's going to leave us with the units of newtons per coulomb. Gravitational field strength would have been newtons per kilogram. This is the electric field strength, though, and it has units of newtons per coulomb. It tells you how many newtons a 1 coulomb charge would feel if there was a 1 coulomb charge at that point. This picture shows us what the field strength is like near the charge. It's going to get stronger and stronger as we get closer to that charge. And it'll get weaker and weaker as we get farther away from the charge. Now, a radial vector is r with a vector over its head. It's going to point from the charge that's responsible for the field to the point at which we're evaluating the field. Let's go ahead and draw the radial vector now. It'll go from the charge to the location where we're evaluating the field. And we can label it as r with a vector over its head. Next, we're asked to find that vector in terms of unit vectors I, j, and k. Now, a unit vector of I points to the right, and it has a magnitude of 1. All unit vectors have a magnitude of 1. This is a picture of I hat. J hat would point in the y direction, and it would also have a size of 1. Now, our vector points to the right. It doesn't point up or down. So our vector is not going to involve j hat. It's going to involve I hat. And so our vector has to have a magnitude and a direction. The magnitude is the 4 meters. That's how long it is. And the direction is given by the unit vector. If you need a review of unit vector notation, go back to my Physics 1 playlist, section 1.1. There will be a section toward the beginning dealing with unit vectors and vector form. The unit vector r hat will point in the direction of vector r, but r hat has a dimensionless magnitude of 1. Can we draw on the diagram above what the r hat vector looks like? Interestingly, it's already drawn there. This red vector is r hat. It points in the same direction as r, but it's shorter. It has a magnitude of 1. If we were to find the vector form of r hat in terms of I, j, and k, in this particular case, r hat is I hat. That doesn't always happen. Our r vector can point in any direction. In this particular case, it happens to point in the same direction as I. This time, we'd like to find our electric field as a vector. So, if we're just finding the magnitude, we would do E equals kq over r squared, and that would be the strength. If we want the direction too, then we have to use the full formula, which is E with an arrow over its head equals kq over r squared, that's the magnitude, times r hat. All right, so how is this calculation going to be similar to the previous one I had done, and how will it be different? Well, all the numbers are going to be the same. But we're going to attach the r hat on the end. Since r hat is I hat here, I'll just do that. In this particular case, there are very similar calculations, but one just shows the magnitude. That's this one. And the other shows a magnitude and a direction. So once again, let's draw and label the r hat vector. And now we'll do an interesting mathematical exercise here. We'll find r hat by dividing r vector by its magnitude. The double lines around a vector mean what is the size or length of the vector. All right, so our vector is 4 meters I. We want to divide by the magnitude of it. And we see that the magnitude of it is just 4 meters. This reveals that r hat is in fact I hat.